I continue to work on the compiler for the Elna programming language. The compiler is self-hosted and uses only the features that are already implemented. And since it is self-hosted, basically the thing on the screen is the language itself that I'm implementing, and I begin to work on a bigger topic that is important, but I probably will need some time to think about a few things about how to implement certain things. And the topic that I'm working on is stack allocation. So my current stack allocation let us find where we generate the prologue. So this is the instructions that are generated for the beginning of each function. So it is a function prologue, and a few lines later function epilogue. And for every function I just allocate a static size, a static amount of bytes, 144 bytes. And there is no difference between functions, so it is allocated independent of how many the function really uses. Some of these 144 bytes are used for the local variables, and some of them are used to save to calculate and save the arguments before passing them to a procedure call. And a few bytes are reserved, for example, to save some expressions, for example, in assignment. So the left side of the assignment is saved on the stack in the static spot, and then the right side is calculated, and then the left side is read from the stack again. Of course, it is only a temporary solution, so we need to make this stack allocation dynamic, so it allocates only so much as a procedure need. So we need to look how many variables a procedure has and allocate the stack only for these variables. And of course, currently the procedures cannot have too many variables because it would overflow the stack. And I assign the stack offsets to the variables to earlier. So I do it, I think, during registering the variables during the semantic analysis, and we need to do it much later so that we can actually after generating the 3 address code and after generating a register transfer language, so a language which looks pretty the same as assembly, and we need to assign offsets in this stage to variables, so we can use temporary variables later for sub-expressions and things like this. The compiler in its current form doesn't support sub-expressions, but having a proper register allocation would allow to to have sub expressions later. Yeah, I'm not sure how much I will spend with writing, because I will probably have to think about what I'm doing. So we will see how it goes. I hope that I will be able to do at least a bit. We actually, prolog generating was a good place, so we did it exactly. So the prolog and epilogue is written when we encounter these allocate stack instructions. So let us see where we create this instruction. So this procedure converts a 3 address code into almost assembly, into RTL, register transfer language, and I also added an additional pass that is run after the generating of RTL, and this pass is called allocation. So we won't do a proper register allocation currently, but probably we will use this pass later for register allocation. So, and now I want to move adding of this instruction into this allocation pass, because we can know how much space we need for the stack only after running this RTL pass, so during this allocation pass, and we will move the instructions to generate them. So here we have an RTL body. I will split the screen so I can navigate better, and we have this body in here. It basically visits all the body. This is basically procedure body, and the body is a list of instructions that are a member of this procedure, or that represent this procedure. And we need to check the stack variable. The stack member of the declaration says whether we need to generate a stack for this procedure. We have one special case. There are auto-generated procedures that return the size of the specific type. So this adjusts auto-generated procedures that are currently needed, and they don't need any stack, so I don't generate a prolog and epilogue for them. And this stack variable basically a boolean that says whether we need to generate a prolog and epilogue for this procedure. So, and it is a member of this RTL declaration. And the first thing that we can do, we can just add the same check. So basically check whether we need to generate allocate stack for this procedure. So and actually we want to do pretty the same thing as we do here. So we just copy the stuff here. We need to define a few variables, I think. The one of them would be this return instruction. Probably we need body, then let us call it stack instruction. It will be the instruction that we generate. And let us see. So this is return instruction, but we also need, I haven't copied the first line as it seems. So we create an instruction. The current declaration body will be, so the instruction list is a list, and every list has a next element, and we basically assign to this stack instruction the current declaration body. So it is RTL declaration, and this is stack instruction. Then we can set the body of RTL declaration to this instruction, body to the stack instruction, and then we need to create, so with allocate stack we generate the prolog. So we allocate stack and save some information on the stack, the return address and the frame pointer, and after that we need to restore the stack and the modified registers. So we create this return instruction and we append it to the RTL declaration body. The compilation will probably fail now because we generate this instruction twice, but it failed a bit too fast. Do I have any errors here? Stack instruction, next RTL declaration body, stack instruction assigned, RTL declaration body and return instruction. If we remove this here, no, it still fails. This body variable isn't used anyway. And if I just copy paste this thing, so let us try it differently. We create a new variable and we call this thing, oh, I cannot reference. Do I need a reference in here? Of course. So the type is of course wrong. The type we need we need an actual type here so that I can dereference the type and calculate the offset. And it doesn't fail. Very nice. So we can remove this one. And if we remove this block, then the compilation should fail. It doesn't fail, but the compilation hangs, so it runs into an infinite loop somewhere. So we need this part, and we can remove this part from here. We just test once again that it really works, and it does. We probably do not need some variables anymore, so we don't need this return instruction. And this body thing isn't needed anymore too. So actually we can just directly assign the result of this visitor to the body. Okay. That looks fine now, I think. So we can go to the next procedure, to the next visitor. So after generating the stack allocation and the allocation instructions, we visit all the instruction in the body of the procedure. And the idea behind stack allocation that we don't assign offsets to the variables right away, but we keep the names of the variables, and then we go to say it differently, we assign not the variables, not variables name, but we save them into registers, but these are not real hardware registers, but pseudo registers. And we need to replace these pseudo registers with real registers in the last step. For that, we need to look into each instruction and into the arguments of that instruction, and to find these pseudo registers and replace them with the real registers. So the function that should replace the pseudo registers with real registers later is this alloc instruction, and it is completely empty now. It gets an RTL instruction as its argument, and the first thing that we will do, we will define a variable kind here. we assign this variable kind to local variable, so we say elna rtl instruction get kind, and we pass rtl instruction to it, and this rtl instruction is really an instruction list, I think. So, and the kind of the instruction is somewhere here. Yeah, this is the instructions that are currently used, and we need check them all, I think. So we read the instruction kind, we try to compile it, so we see whether something changed. So it compiles, and now we just need a long if-else statement so that we check all the kinds that we currently have. And it will look like this. So we say that if kind is elna rtl operator leave, for example, then do something. Else if kind is elna rtl operator load address, then okay, and then we just copy the other instructions. We do not need allocate stack and return, I think, and label also not, and jump not. So we don't need actually all instructions, but we will copy this in here. So which instructions can have pseudo arguments? At immediate load word has the target address as register. Stalwart jump and link. Jump and link has only a symbol, I think. Yeah, jump and link instructions generates currently the call instruction. I haven't said the target hardware or target CPU of the compiler is RISC-V 32-bit. Call is a pseudo instruction in RISC-V. The actual instruction is jump and link and something else. So call can produce multiple instructions, and it currently expects only a global symbol, so it can't have any register arguments. Then we have move. This is basically a sign. It has two registers: sub, divide, reminder, multiplication, XOR and OR, and set equals 0. This needs two registers. Set not equals 0, set less than, sorry, negate not, they need registers. Jump is an unconditional jump. And it has one argument. I wonder why when I do generate jump. So I use the same argument for 3 address code jump and for assembly jump. So here I always use a label, so it's basically jump if 0 is different, jump, and here it is a label again, so it is not a register, I think. Now I think that I always jump to labels. Then we have branch equals 0 and branch not equals 0. They check a register for a value, so they will have a register argument. And now we just copy this thing. Yeah, I should install someday beta editor. So I'm working in a virtual machine, and it kind of was pretty difficult to get Linux running on RISC-V, because Linux distributions I know only have support for RISC-V 64-bit, and I have the 32-bit version, so I had to build Linux myself. And this editor is actually, I think, Elvis, so it is not Vim or NeoVim, because Elvis was pretty easy to build. I don't know how difficult it would be to build something like NeoVim, because NeoVim needs all kind of stuff like Lua and whatnot. And Elvis is a V editor, but it's lacking a lot of features. So the editing is not always that easy. Then we have and. Set not equal, set less than. Oh, this doesn't look right. Do I have, sorry, no. Okay. Negate and not, negate and not, and when we have two branching instructions, and that's it. So we will try to implement these pseudo registers only for one operation, so we can test the approach itself, and when we can extend its usage. So basically we need to replace this ELNA binary arithmetic call with the actual procedure call, so that I can modify it. I only need to find the declaration of this thing, and this is actually the declaration. So is there an easier instruction. So actually binary instructions are more complicated than they should be. We can just take something unary because they have less operands. Something unary. Something unary would be stuff like not, but I'm not sure that I'm using not somewhere. But I'm using minus, for example. But minus can be used pretty often, but in most cases as binary operator, not as a unary operator. The operator should be also used so that we can see whether it works, and I don't really use unary operator somehow. So it doesn't matter, let us go for this, for the multiplication. Exactly, we just need to replace the procedure with the body of that procedure so that we can modify it without modifying code generation for all other instructions. And the result is LHS, so we can put a comment around it, and we can rename this LHS variable to result. We do not need to return anything. It won't probably compile because I suppose here will be undefined variables. Result, binary result. Binary operands. This operation is ELNA-ATEL operator multiplication. It's actually should be pretty the same as the thing that we see here. No. Arithmetic operation. Oh, I still need to replace this operation with a multiplication. This is actually nonsense. I set the kind of this operation here, and then here once time again. So if I remove this one, then it compiles. And if I remove this line, this shouldn't be needed since some duplicated code that we can remove. And here we set both registers to real hardware registers. We can remove this line. Now we still call this ELNA ETL binary operands procedure. Let us look at its definition. So it converts two operands to a set of instructions and saves the values, the left value into 2 and the right value into T3. We can copy this stuff again. So the thing that is returned from this function is LHS. That means that LHS becomes result. And for RHS we can use some variable that we don't need. For example, this intermediate instruction, is it called? So we replace intermediate instruction and so, and that should be it. That compiles, so we can remove this thing here. And now we only have two calls to this ELNA RTL load operand value. And this is actually the procedure that is interesting for us, since it replaces immediates and such and stack variables with registers. We can just change the meaning of this procedure for one of these arguments, so that we don't save the registers itself to 2, but some kind of a pseudo register or a temporary variable that can be rewritten later. I'm thinking whether I should just copy this procedure and modify, or copy its body. So you just need these three variables: operand value, operand length, operand value. Let us create an additional procedure that we call RTL. Let us call it just multiplication, and we copy the arguments. I think the arguments we need are basically the TIC instruction and this instruction list. We will need a result variable. I should only look what its type is, just what. It's probably an instruction list, a pointer to an RTL instruction list. Let us just exactly. So let us move to this. Let us move to the code that we want to copy into this procedure. So it would be the whole branch here. We insert it in here and remove some indentation, and we need a few new variables. Next instruction is for 100, then we need this operands variable. Let us try to compile it. This one shouldn't work actually. Next instruction, operands, intermediate instruction. What do we have else? TIC instruction. Of course it is run. So for example, this intermediate instruction is actually an instruction list, and to be fair, the result is also an instruction list, and the intermediate instruction is an instruction list. So now we go to the multiplication. I hope that I can just remove this stuff here altogether. I should return this result at the end. And instead of all this block, we just call this procedure and assign its value to the result. So we just say elna RTL multiplication, it gets the TIC instruction and the next instruction argument, and assigns its result to the result variable. And now we have this one procedure there where we can experiment a bit. So We now go into elna rtl load operand value. And we will define all these variables here as well. So we only need these three, I think. And now, so result here will be the left side of the multiplication. So we just get all this thing here, and it uses result as variable as well, and we paste it here, and then the returning can be removed, and theoretically I can remove this one, and it basically just, what is operand number? Operand number was 2. The first operand is of course the target register. So we can replace the operand number. Let us use a variable for that so that it can be easily changed later. You basically just say operand number is a word, and operand number is basically 2, for example. Then we have this done, and then it just checks for different kinds of types for this thing. Will it compile? No, of course no. So what is missing? We have then this next instruction. How is it used? I think it isn't used. Yeah, it isn't used properly. So it is used as some kind of temporary variable, but we do need it. So we replace it with intermediate instruction 2. Next instruction intermediate. Next intermediate. Result. Operand value, operand type. How it is called. And it has a third argument, that is the register T2, and this thing is saved into variable, and we define it as well. Let us put a comment here so we can find this later. Test values. So it compiles now. The case that is interesting for us is this stack case, because stack means that it is a local variable. To see whether it is used, we can remove this block, and if the compilation fails, and it does, because the compiler hangs, then this is used somewhere. So I generate a lot word instruction so that the value is loaded into the register. But what I actually want that this LHS, or the multiplication, isn't a register, but a pseudo register. How do I achieve this? So this is the final multiplication operation. We can say that the result in this case is nil, so that we don't generate any generation to load the value from the register. So we basically say that the result is nil. And here we generate the instructions for the right side of the multiplication, and we assign this as next instruction, so result next can be nil. What is if result is nil? The next instruction would be an intermediate instruction as well. Result should be set as well because it is the first instruction in the list, and if LCS is not an instruction, that then the first instruction is RHS. And here we assign then intermediate instruction next is the next instruction. To be honest, I can't of doubt so we revert the changes. I doubt that this thing with two different symbols actually works. It could be just that the code isn't executed, but it looks pretty wrong to me. So it just never executed. So we can remove it again, and this actually should be single dereferencing. Result intermediate instruction, that's fine. But then we have a different problem here. So what is actually the operands? the operands is created here. I can create it before. And then I can set the second argument. So we do not need to set it here since it isn't executed as it seems. But in this case, basically, and in this case, we can write sudo here. A little test would be if we now go to this, what was it, allocation instruction function. That function reads then the multiplication operation that we generate. And let replace. So we are replacing the second argument of the multiplication instruction with a pseudo register, and we need to read the second argument then from the instruction again. So we add these three variables here as well, and we read their values from the operand. So these are basically three properties of each operand. This won't be TIC instructions, this will be RTL instructions. And the operand number is 2. The second one. So we can actually I doubt that it was useful. Let us add an additional test step. So we generate this instruction. We will move the generation of the instruction later to the next pass, but we mark it somehow that we encountered a variable. So we said basically this is variable to 1 in this case, otherwise we set it to 0. And we do not need this if condition then, so we can just do it later. Set operand 2. Let us remove this thing again. And let us remove this one. So here we say that if is variable is true, then for the second argument we do not, for the second operand we do not set it to a register but to a pseudo variable. Oh, it should be the other way around, of course. Pseudo and register. Yeah. And we get a bunch of invalid instructions. They are invalid as it seems because the second argument, the second operand is an immediate, also an 8. And we need to check it here. So basically if we see that the operand type is elna rtl register pseudo, then we just overwrite it with the register, so it should fix the compilation again. So basically we just say that elna rtl instruction set operand, and we rtl instruction, it is the second operand, we set it to rtl operand register, and we set it to a constant value of t2. Now the compilation works. So it isn't actually what we need or what we want, because we still just fix the register kind later, but it is just a test that we get an instruction in the TAC, in the 3 address code, and that we can fix this instruction during this allocation stage. And now we can basically move the usage of these registers from this RTL stage to the allocation stage. And I should think what would be the next. And actually the next thing that we can do, we can really, so here if we see this, if we see that this is an offset, then we generate an additional instruction that that loads this offset, the value on this offset into the register, and we should move this loading step basically into this allocation path, because the allocation path should be responsible for allocating registers. So let us generate a new instruction. We add a new variable, load instruction of type word. This can be actually elna. What are they called? Elna instruction list. So, and what we are going to do, we are going to generate this load instruction here, and we will say that load, did I call it load instruction? Yeah, load instruction it is. Load instruction is elna RTL instruction create, and it is a load instruction operator LW, and this is a load instruction, and we can set its operands to the same values as here. So we can just copy it from here, probably. So the result is this load instruction. We set the first and the second argument. So load instruction has two operands: the target register and the source. What is the operand value in this case? So the register is the stack pointer, and operand value is the offset from the stack pointer, and the offset is correctly in the operand value, I think. Operand, the value will be here, the register, so we do not have the operand value at all in this case. We do not have the operand value at all. Numbers 2. Operand value of the second argument is saved basically here, so we can set not only to 2 here, but also override the value. So we write the operand value here. It is an offset. No, it is not. This is this stack type, I think. Yes, this is stack. That means that offset is set in this value variable. We can pass it in here. Then we can read it, and then we can generate this instruction. RTL set operand 1 2. That for instruction, the instruction. This is the new one. And I want to set this variable into T2. But it actually only works because we prepend this instruction to the beginning. Let us first to prepend this instruction. How can we do this? So we get an instruction list, and this instruction list knows its next element. We have an RTL instruction, and we want to prepend another instruction to it. I can modify the values of this instruction, so I basically have to write it. I think we can define something like next instruction and say that next instruction is also an ALN instruction list, and we can assign current instruction to this next instruction, so RTL instruction, because because we need to prepend loading value to this instruction, and then we need to set all the values not on the load instruction, but actually on this RTL instruction. So basically we can do it. We can set kind of RTL instruction to load. I hope that the procedure does exist. Elna RTL instructions set kind. Yes, it does exist. And we set its kind, and we override its operands. So this goes then into RTL instruction. The first and the second, that should be fine, and then I need to reallocate the previous instruction then. So I have an allocated instruction. I replace the values into allocated instruction, but I need to copy the current instruction into a new one. I know that the current instruction is a multiplication instruction, so it has 3 operands. I can just return the new instruction here. Or pass actually a pointer to the list. Or I can copy the operands. Let us do it the simple way at first. I doubt that this is that simple. Create. So we need a new instruction. This new instruction will be the same instruction that we already have, because we want to have a copy, and we need to copy all fields of this instruction. I can just copy it. I think this is actually the easiest, and we know the size of the instruction, so I can just allocate some memory with malloc and say that exactly I want to allocate some memory. This will be this lot instruction, and then I can just copy the original instruction into this lot instruction, and its size is basically this much. After that, I can reassign one of these instructions, so I can get the first instruction, or we can actually change them again, since they are basically the same. But yeah, this is correct. So we change then the current instruction to the lot instruction. We set its arguments, and we set the following instruction to set next of RTL instruction. I don't need this function. Do I have this? RTL instruction set next. I probably don't need it. I can just say RTL instruction next, is the copied instruction. So basically this load instruction, then we chain them, and the load instruction has a pointer to the next element copied from the previous instruction. This should be not needed anymore. And here we just reset the argument, but because we copied with this instruction, we loaded the value at offset into T2, and here we need to replace the operand in the copied instruction to the appropriate register. Okay, let us go to this ELNA RTL operator mul, and exactly so, but it should actually work. It would just generate a second instruction with the same value, but it should still kind of work. So let us go through it again. We do not need, let us rename this load instruction for a bit more clarity to the old instruction, or original instruction probably. Let us just call it old instruction. So we allocate memory for this old instruction, we copy the source instruction into this old instruction. This next instruction isn't used at all, I think, so the variable can be just removed. Okay, that looks fine now. So yeah, unfortunately it goes very slowly, but after we finish one single instruction, it will be pretty simple to migrate all other instruction, I suppose, because they actually use all the same functions for the register location. So we just need to move this register location to a later pass. And we achieved currently that I can set a so-called pseudo register in the RTL generation pass, and that this operand will be then fixed in the allocation pass, and that the new instruction will be added that loads this pseudo register value into a real register. So next time we can look into that we do not pass a stack of set as a pseudo register, but that we generate a value for the pseudo register or use the variable name, and that we generate the offsets later and replace the pseudo registers that with or the load instruction that loads a value from this pseudo register that we use their some names and not the real stack of sets, so that stack of sets are generated later during this allocation pass. But for today we will finish here.